Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Today, we will start with a few questions to wrap up a little bit. Then I'll continue with this lecture on data models. If time permits, we might start with MapReduce, but we'll see if either today or tomorrow. So let me switch over to this question. It's about HBase. So there is a conundrum here, because I told you that HDFS has a high latency. Whenever you execute a command, it's not instant. And yet, HBase is much better. HBase can do updates in place, update small values, query small values. It's random access, but HDFS is not. So latency, let me summarize. High latency, no random access for HDFS. Lower latency and random access for HBase. How can it be? Since we saw that HBase is on top of HDFS. So you would think maybe it's constrained by HDFS, and actually not. So why is that? Is it that first, HBase is not faster? I'm just telling you things that are not true. It has high latency like HDFS. Or maybe it's because it has key values in the name store as well as caches. Or is it because it short circuits the data nodes? Or is it because it uses smaller HDFS block sizes, 64 kilobytes and not 128 megabytes? Right, we have a few answers. And these are the two correct answers. It has to do with these two things. First, it doesn't only use the disk, HDFS, it also uses memory. All the freshly created key values, they are in memory, not yet persisted to HDFS. It's only when they've been for a while that they start being persisted to HDFS, right? All right, and the other thing is that it short circuits data nodes in the sense that you can directly read, if you happen to have a copy of the HDFS block on the same machine, on the same disk, then you can directly read it as a local read, and you don't even need to go through the network to get the data. All right, short circuiting, we'll see it again with MapReduce, right? It's really something that we'll see with different technologies. I have another question right here. Which is better? XML, JSON, they're equivalent, or it depends on the use case? Take a look. Okay, we have a majority there. This is indeed my favorite answer. I'm not saying the other are wrong. There might be people who prefer XML, people who prefer JSON. It's a matter of taste. You're also right that they're equivalent because both represent trees, and you can convert when it's data-oriented very easily from one to another. The only exception is when you're using, for the publishing industry, texts like scientific papers that are annotated with XML. This is the one use case that you cannot so easily convert to JSON, right? But this answer here depends on the use case is actually the answer to many other questions. Do not assume you're computer scientists, so you might think Emacs is better than VI, or I don't know, Linux is better than Windows. You really need to have a mindset of it depends on the use case. It depends what you want to be doing. In some cases, XML might be better. In some other cases, JSON might be better. It depends what you want to do. It depends on the features that you need to have them in the stack, and so on, right? Okay. Well, except for Emacs and VI, Emacs is actually better than VI. All right. Joke aside, let's go back to the slides. All right. Okay, so we were in the middle of JSON, the first schema language that I introduced to you for validating JSON data. Before, I want to make very clear something that I've already told you. There's well-formedness, which is about, can I open the JSON file? Can I parse it? then convert it to a memory representation as a tree. And then there's the second question: is my JSON that I might already have put in memory, is it valid against the schema? The schema is extra constraints that come on top of well-formedness, and that assumes structure about the document. For example, in that case, I have a schema below, and you see that I require a key called guess that must be a string. I require a key target that must be a string, a key country that must be a string, a key choices that must be an array of strings. I require a sample that must be some binary format. You see it's in base 16, you see it over there, and a date that must be of type dates, meaning the ISO 8601 convention with the dash separated year month dates, right? You remember the exclamation mark here is for required. If you don't have the exclamation mark, it's optional. If you add the exclamation mark, it's required. This here is the compact syntax of JSON, and that's a pedagogical goal. It's that this resembles the document, right? You see how intuitive it is between the schema and the document. There is also another syntax that is verbose, but this one is not really part of the material. I just told you it exists. Basically, the compact syntax can do 90% of the cases, and then the rest 10%, you need to switch to the verbose syntax. For example, if you have special characters in the key, like an exclamation mark that is actually part of the key and so on, right? Or if you want to allow for additional keys in an object, that's also with the verbose syntax. But in many cases, you can just do with this syntax here, okay? And we left last week on this slide, where this is just a list, a feature list of the sort of things you can have in schemas. You can restrict values to a specific type for certain keys. You can also implicitly cast, meaning that you can have a date, for example, doesn't exist in the syntax of JSON, so it would obviously have to be in a string. And if you specify a date type, then what happens is that in the memory representation, you have an actual date, a Java date or a Python date, whatever you are using as a host language. Then you can also make a value required, a key and a value required. You can also say whether or not you accept keys that are not in the schema. You can go either way. That's called opened and closed object types. You can specify a default value. It means that if it's missing in the JSON, you can automatically add it as part of the validation and annotation process. And then in memory, you will have it set to the default value, right? And then finally, you can also support primary keys, but that I didn't go into. You should just know that many schema languages make it possible. For example, in that case, you would have an array, and foo here must have a different value every time because it should be the primary key of these objects. And here it would be an example where that's broken. All right, but that I didn't show you how to do it because that's again beyond the material. Just know that it exists. So you might remember this JSON that I've showed you last week as an example of JSON that is kind of easy to validate in the sense that it would be easy to build a schema against which it validates. And here is the schema, right? You see it's very similar to the document. So I put a required A, which is an integer. You see it's 1 here. Required B is a Boolean. Required C is an array of objects that all have a required key foo and an optional key bar. You see here it's actually missing. Here you don't have any bar. And if it exists, then it must be an array of, I put long, but it's arbitrary that I put long here, right? An array of longs. And now to clarify, because there was the question last time, the fact that we have a required foo here, does it mean the array cannot be empty? No, the array can absolutely be empty, right? If I have here an empty array, it is an array of objects, just there is no limitation on the cardinality. So when I say foo here is required, it's really required for all the objects that exist. Foo is required, right? But it's totally possible that there is no object at all, right? If my array is empty. All right, so this is the instance, and this is the schema. Who now has a good intuition of JSONs, at least for these cases? Okay, very good. Now I have a perk for you. You can go to that page. It's actually a public instance of RumbleDB that's running somewhere in the cloud. And you can actually also connect with via Jupyter Notebooks. But technically, there is this page here. If you add /jsonvalidator.html, then you will land on a page where you can put an instance on the left and a schema on the right, and then click on validate, and it will show you either green light, this is valid, or these are the errors in your document. So,
You have a question?
Yes?
Thank you. I would like to ask if there's a way actually to validate the cardinality. Like this is to say if it's required or not, but if there is a possible way to validate the cardinality.
Yes, in the verbose syntax, yes. So in the verbose syntax, you can create an array type. You can say that every member of that array must be an object that looks like this, and you can specify a minimum number of members and a maximum number of members. So yes, it is possible in the verbose syntax.
Okay,
yeah.
Thank you.
Thank you. All right, so this is for you. In fact, if you have Docker and the RumbleDB inside the Docker, that might even work inside of your Docker. The /JSON validator trick will open the page. Just a few words of warning. If some of you want to directly connect to this cloud instance because it doesn't work on your machine, be careful because the machine on which this is running has 1 GB of RAM and 1 or 2 cores. So it's very small machines. There's 4 or 8 of them. It kind of scales a little bit depending on the users, but just be warned that this is a very small instance just for playing. It's not meant for production use. All right, but this is it. This is what you can play with if you want to train with JSONs. All right, and by the way, this was contributed by students, by your predecessors in previous years, both the page and the implementation of JSONs in projects. All right, so this is JSONs for a smooth intro to schemas. Now there are others out there. JSON schema is another one. So I will show it to you, but hopefully you see that the features are the same. It's just that the way it works in syntactically is a bit different, but now you know how to validate. That should actually make sense. In fact, it's a bit similar to the verbose syntax of JSON in some ways. So this is JSON schema. JSON schema works like this. It's a bit more complex, so it doesn't look like the document anymore. So we say that we expect an object, so type object, with the following properties. Last, the type of which must be a string, right? So it's kind of Shakespeare JSON in the sense that it's more verbose, but this corresponds to here last Einstein, and the instance above here is valid against the schema below. All right? Then you can have several properties like this by listing them, and both are of type string. You can also make the same assumption. This is the same as in JSON, that if I don't say anything, then my keys are optional, right? So here I could omit first. You see, it's no longer there, the first key. And first in the sense of FIRST, it's no longer there, and that's fine. It's totally valid because by default, it's optional. If I want to require them, instead of the exclamation mark in JSON, the way it works here is with an additional required declaration with the array of the keys. So here we say last and first. So these two here are actually required, and then they are forced to be here. All right. Now, a bit of vocabulary. You probably noticed that instead of keys, they call it properties, right? So here it's a little bit like what I told you about blocks, splits, chunks, shards, partitions. Here it's the same. Keys, properties, fields, and so on and so on. So just be aware that you might encounter many, many ways of calling them. And in that case, we call them properties, right? But just don't be scared by that. It's only vocabulary and different conventions. All right. Extra fields here by default are allowed, right? In JSONs, that would be closed by default. But here it's open by default, meaning that if I have extra properties that are not in my schema, this is totally fine. If I don't like this, I can forbid them with additional properties false, and then I'm going to restrict my objects to only have last and first. All right? So you see that the diversity of the schema languages, they do the same things, but the default behavior might vary a little bit, right? Now, in terms of type system, JSON schema doesn't have such a rich type system as JSON. In JSON, there's this very long list that I gave you with maybe 20 or 30 different types that you can have. In JSON schema, you don't have so many types. You really have the basic ones like a string number, Boolean null, object array, and that's pretty much it. There might be a few extra. It might be that there is an integer one. But basically, everything additional to further specify what a type is done based on additional constraints. You cannot even have a date, right? You really have to say it's a string and it has the format of a date. That's how you would do it. So just so you're aware that it's a bit more involved in JSON schema, right? So you have number, Boolean, so all the basic JSON types you have and you can use, right? So number, Boolean, null. All right. You can also allow any value by using the value true. So here it's completely arbitrary that it's done like that. There is no logic. It's just the decision, the design decision, right? So if you associate some key here, some property with the Boolean true, it basically tells you you accept everything. So location, anything you put there could be an array, an object, a number, anything, it would just be accepted. And false is the opposite. False, you completely forbid that field, right? Why does forbidding make sense? Because in that case, remember that it's an open object type by default, so it accepts any properties. So what you're doing here is you can have any property you want except location. That's what it tells you, right? Anything except location, plus if that property is last, it must be a string. That's the semantics. All right, and you see what I told you about additional restrictions. You can also do it in the JSON verbose syntax, but just to show you, you can specify a number. The minimum is -90 and the maximum 90 for a latitude, for example. And for the longitude, it's -180 to 180, right? So you can specify these boundaries. And for arrays, it looks the same, right? In an array type, you can also define a minimum and a maximum size, right? So in JSON schema, in the JSON verbose syntax, in many schema languages, you can do these sort of things. Even in XML schema, we can do this, right? So these are really generic features that many schema languages have in common. You can also define an array. So it's not just about putting some square brackets as in JSON. It's a bit more complex, but you just say type array in that case, and that gives you an array of pretty much anything you want, right? Here, it's really a mess with a number, a string, a null, and so on. If you want to say an array of something specific, then you can add that constraint and say, now I want integers, right? So this is what I told you, that it doesn't have many types, but it does have integer in addition to number. It's one of the few that it gives you. Okay, for whom does that make sense? All right, JSON schema, you can use in Oxygen. Who downloaded Oxygen already? Many of you. So JSON schema you have in Oxygen. So you can really open Oxygen and play and put some JSON and put some JSON schema, and it will check for well-formedness and for validation. All right. And now I'm moving on to XML, even though I'm not going to spend too much time on XML, because as I told you, I'm going more in the direction of JSON more and more every year, and the XML content is diminishing as we have equivalent features in JSON. But the good news is that since we covered JSON validation, I'm pretty sure that by now you pretty much already have an idea of XML validation, right? Because that's the same idea, right? In particular, we'll have a schema. You can have a well-formed XML document that has been parsed and put in a memory tree representation. And then you come with an XML schema and ask, is that document, this XML document, valid against my XML schema? And I have an additional good news, is that just like JSON and JSON schema are actually expressed in the JSON syntax, you can see that XML schema is also expressed in the XML syntax, right? So that's one less thing to learn. Now, to simplify things a little bit and to not scare you with details, the instances I'm going to validate here, they won't have namespaces. I'm not even telling you how I'll say a few words, but I'm not going to show you any examples of instances with namespaces. So here, no namespace. Remember, if there is no XMLNS, then there's no namespace at all anywhere, no prefix, no namespace. But it doesn't mean that the schema itself doesn't have a namespace, right? But this you're familiar with now, right? I'm basically saying that this is my XML schema namespace. This is the one specified by the World Wide Web Consortium. That's how it is, right? It's just this, namespace. And I'm associating with the prefix XS right here. And now I'm using XS at a lot of places. Even here, that's actually new, but even the values can be prefixed to be qualified, right? All right, and you might also see XSD, which is another prefix that some people use, so can be XS, can be XSD. Some people create the schema declaring the XML schema namespace as the default namespace. Then you don't have XS schema, you just have schema. I strongly recommend against it. This is going to create a lot of confusion between when you don't have a prefix, is it in no namespace, is it the default? It creates too much confusion. So never create a schema putting this in the default namespace. Always put a prefix here, then it's very clear what is in what namespace. So you see in particular that in XML schema, all of the types, it's the same type list as in JSON, the same one. So you don't have anything more to learn. String, integer, double, float, and so on. All the atomic types are the same, but just in the namespace, so XS string. So now we're saying we have an element, the name of which is foo, and the type of which is string, which is in my namespace. And here I have indeed a string, right? This is text, that's the string. Foo is indeed element foo. So this is all good, it's valid. Now I'm going to show you a few more examples. Here it's type integer. You can just put anything from the list, this long list of types that is common to JSON, JSONic, and XML schema, all the atomic types. And in that case, it's valid, you see. This integer, 142,857 is indeed an integer. By the way, it's called the Phoenix number. Who heard of this? Try to multiply it with 2, or with 3, or with 4, or with 5, or with 6, and see what happens, just as an offline trick. All right. But anyway, this is an integer, and so I do have an element foo with an integer inside. So you see the magic that happens now, because when I introduced XML to you, I told you there's text. The only thing you have is text. But with the power of XML schema, we can turn that text into any type we want. We can make it a date, we can make it a number, an integer, binary data, and so on, just by validating. And what happens then in the memory is that you will no longer have text in the memory representation. You will have an actual integer in Java, in Python, or whatever language you're using to use XML. So this is about atomic types, right? If I just have a simple element and I put some atomic type inside. What about complex contents? It means nestedness. So here I have in my instance a person with nested elements, last and first, that are nested within person. And the way I do that is this with super scary, complex, verbose XML content that I just dropped in there. And that just happens to be this way. You're basically declaring an element, the name of which is person here. And then you're saying it has a complex type, because yes, it looks very complex here, which is a sequence of 2 elements in this order, last and then first, you see, last and then first. And the type of last is string, and the type of first is string, right? String, string. So for whom does that make sense? Apart from the very scary and verbose XML schema. All right, good. Now, what about repeating elements? Because I told you in XML, you might repeat elements. In fact, it's a common pattern. I told you, you have the outer element that is a plural form, like persons. And then within, you have singular elements like person, 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 person. So how do you repeat? When there are the magic words, I'll come to the question on Zoom right after that. Min occurs and max occurs are the way you control the number of times it occurs. So here I called an element 2 to 4, and that logically I allow it to occur between 2 and 4 times. In that case, 1 to 3 times. That's totally fine, right? It's between 2 and 4. And it must be a string every time. That's a string, that's a string, that's a string. Not very original, but it's still a string. And now the 0 or 1 is either 0 or 1, right? Not more than 1 and not less than 0. And this is a Boolean, right? It says Boolean true. Is there a question?
Yeah. So does the order matter here? The last comes before the first?
Yes, the order matters. Yeah, absolutely. That's the difference. In JSON, there is no order in the objects, right? It's just a map, so it can be in any order. Even though, as I told you, most of the implementation will be nice to you and nice to human users in the sense that they will not shuffle things around and keep the same order. But semantically, there is no order. In XML, it's different. In XML, there is an order, and it must really be first 2 to 4, 2 to 4, 2 to 4, and then 0 to 1, exactly in the order as specified here. That is a big difference. So if I swap, it would be invalid. That would no longer work. There are advanced ways that I will not show you in XML schema to say, I don't want any specific order, but this is really advanced, right? So I don't want to scare you with that, right? Okay. Now, what if I want something empty? Well, I just put sequence slash and nothing in the sequence element, right? Here I had my sequence element with 2 elements. If I just put a slash here, I'm saying that's empty. It's an empty sequence, right? So here I have foo. That is empty, and this is valid against this type. I didn't put the whole thing because I should normally also have put here schema, element, and then inside the complex type. I just took shortcuts. Here I only put the complex type, but you really have to imagine that it's nested in element and schema, right? Same thing here. This complex type here is here, nested in an element in a schema, right? So this here is valid against this complex type right there, which says that it's an empty sequence. Remember the slash at the end means that it's an empty element. At the beginning, it would mean that it would mean it's a closing tag, right? This is a closing tag. This is an empty element. What do I have here? Mixed contents. This is for the publishing industry. This is the case where you have very long scientific papers that you stored in XML, and because you want to display them maybe on some web page to the users. The way you do that, some text and some bold text, and I put this bold annotation in there, kind of HTML-like. This is done with this magic attribute right there, mixed true. By saying mixed true, I basically allow these elements, like B, for example, element B must be a string. I allow it intermixed with text, right? So I have here some text, then my element B, and then some more text, right? So this is what the mixed true is doing. This is the one thing you cannot do in JSON, right? So this is the one use case for the publishing industry that XML is doing something that would be, I'm not saying impossible, it's always possible, but very, very tough to do in JSON, very, very cumbersome. Okay? All right. What about attributes? Well, I can add them after the sequence declaration, right? After the sequence, I can say attribute birth here is a date. You see, that's part of my very long list of types that is, again, common to JSON, JSONic, and XML schema. It's a date, and you see birth here is a date. So that's how you restrict the type of an attribute as well, an attribute value in this way, and how you say that the element person can have an attribute called birth. I will not show you, but just mention that it's possible. You can require an attribute, you can make an attribute optional, you can have a default attribute value, meaning that if it's not there, it's automatically added and so on. So there's all these fancy features, right? So this is the great language game, the same I had earlier. Let me show it again, right? In JSON, converted to JSON, where is it? Here, that's the great language game, right? Converted it to JSON. No, it's the opposite. It was in JSON like this, and we converted it to XML as an example. So this is the great language game. And now if I go all the way to the XML version of the same thing, it's just we made that up. We have guess target country, the choices with what I told you about this plural singular, right? Typically you have a plural form for the outer element, and then a singular form for all of the nested elements. This is how you have nestedness, right? Typically a table in XML. All right, and now you see this is an example schema where you have an element guess target of type string, and then country, then choices has a nested complex type with itself choice unbounded, right? This is how you allow all of these choices. And then the attributes sample, blah, blah, blah. It's arbitrary, right? But the sample ID, which is the hex binary, we decided to put it in here because it's some kind of ID, right? It's common in XML to put the IDs as attributes. All right. So this is just a final example to show you what the schemas can look like. Now, what about namespaces? I don't have any slides for you, but it's actually pretty simple. If you have namespaces in your instances, which you should, if you are in production, you should have everything in namespaces, then you just declare one schema for each namespace. One namespace, one schema file, right? So if you have 3 namespaces, then you have 3 schema files, and then they just connect with each other, right? You can nest a namespace within the other and so on. I'm not showing that to you, but basically this is very nicely structured where you can declare your namespaces. And typically, you can put them on the internet. Typically, when you have a standardization body that has a schema that people can use, it will put a specification, and it will also put the schema files, and anybody can download them and use them to connect to their own files, right? So this is really something that is web friendly. Let's put it. Okay. What I have here is only for the geeks like myself, that you probably noticed that XML schema is an XML document as well. So either you can see a schema here, or you can forget that it's a schema and just treat it as an XML document, right? Because this is also an XML document. So it can be seen as an XML document in the namespace XML schema. But here, it means that that XML document is valid against itself. You see how cool that is? This is self-describing. This document is validating itself. So you see there's an element called element, and element validates against that very element that it is inside. So again, this is just for the geeks, that this is a very nice self-referential loop that we have here. And the same goes for JSON schema. JSON, you could also declare a schema that is, if interpreted as a basic JSON document, would be valid against itself, seen as a schema. All right, but this is just for fun, this one. Yes? Mm-hmm. Go ahead.
Thank you. So what if you deny an attribute in the JSON schema? Wouldn't that not make it self-validating?
I'm trying to, so an attribute in JSON?
If I like negate an attribute with the same name as the attribute I give, wouldn't that not be self-referential?
Oh, yes. So you mean that you're trying to build Gödel's incompleteness theorem like schemas, right? So yeah, it can be very
false.
Sorry?
If you just put false.
Exactly. Yeah, I'm sure you could achieve that. In that case, though, what I'm showing to you here is really something you find on the internet, because this is the official schema of XML schema. So of course, when they do this, they are not going to try to create these contradictory loops to make it not work, right? So they will obviously give you something that works. But yes, if you want to play the game of, can I create a document that is valid against itself, or a document that is self-contradictory, you could probably find examples. Yeah, but it's really for fun. If you do this, this is really beyond the scope of XML schema. But it can lead to very interesting theoretical computer science questions. Yeah.
Thank you.
All right. Thank you. Okay. So you see, these were not so many slides about XML schema. I scared students in the previous years with many more slides than that. But I hope that what you see is that it's really the same. XML schema, JSON, they all do the same things. They restrict some elements or keys to be associated with specific structures, with specific types. You can make an element or an attribute or a key required. You can create default values. You can recursively specify structures. I mean, this is what schemas are basically doing. All right. And XML schema is not the only one. There's also schematron, relaxing, or relaxing. I'm not sure how they pronounce it. So there's many, many other schema technologies, but they all have in common that they have these features, right? The way they do that might be different, but the features are the same. Any questions so far? All right, then I'm going to move on to data frames, which is kind of a buzzword these days, if you think of the Pandas library. And what I'm about to do now is a connection between JSON validation, with JSON in that case, and data frame. I'm going to show to you that a data frame can be defined on top of valid JSON in specific circumstances, right? So let's go for it. On the left, you have a JSON schema that says, I have an ID that is an integer, a name that is a string, and living that is a Boolean, right? You might remember that it's closed by default, so you do not allow anything else than that. However, they are optional because there is no question mark, right? So it could be empty. On the right here, you have a nice drawing that I call a data frame instance. It looks like a table in that case, but we'll see it doesn't have to be a table, where you recognize ID, integer, name, string, and living, Boolean. So you see that with JSON, you can very easily define the structure of, in that case, a relational table, right? In fact, you could directly map this to a SQL create table statement with attribute names and types with the corresponding types. They might not be called exactly the same in PostgreSQL, but this is the idea. For whom does that make sense? Right? It's very easy, right? 3 keys or 3 attributes, depending on what you want to call them, with types, and this is a specific instance. What you need to understand is that what we have here are 4 different records. And if this is in JSON, this is 1 JSON document, a second JSON document, a third JSON document, and a 4th JSON document. This is a collection of 4 JSON documents. But because these 4 documents are valid against that schema, I'm able to display it nicely as a table like this. Right? This is why I can do this. I cannot always do it. It might be that there are schemas that are too complex, right? That I cannot draw it like this, but in some cases I can. Who would be able, if I ask you to write down these 4 documents in the JSON syntax? Right? Most of you, right? It's ID 1, name Einstein, leaving false. ID 2, name Mirzakhani, leaving false, and so on and so on, right? But you see that with the power of validation, we managed to lift ourselves up from the syntax and into some nice logical representation, in that case, in the form of a relational table. This is the sort of things you get with schemas. You can actually get to this higher level of abstraction. Let's do the same now, but instead of a string, I'm taking an array of strings. Now that's definitely no longer a relational table, right? We are no longer in the first normal form because the types are no longer all atomics. Name is now a structured types, right? It's an array now. It turns out that I can still draw that in some way. It's not going to be a table, but I can still do it like this. Here, I just have my document, and then I put them vertically, like Albert Einstein, and I pile up my strings. Who would be able to give me the JSON documents corresponding to this? Right? Most of you, I guess. So ID 1, name array Albert, Einstein, leaving false, and so on. Then the same thing here. It's an array with a singleton value. Then again, here an array with 2 members, and here the same with an array with 1 value. Okay. The name for that generalizes the table is data frames, right? In data frames, we can have things like this that are not quite a table, but with nested array structures that look like this. What about nested objects? We can also do this. So now it's also not in the first normal form. It's also not a table schema. Now inside my key name, I have a key first and a key last, and both are strings, right? This is also not a relational table, but still I can do something like in the headers, drawing in this name column. I split it into like this horizontally, first, last, and then I basically have ID 1. Who would be able to give me the JSON object? Okay, most of you. So it's basically ID 1, name first Albert, last Einstein, leaving false. And you can do the same with 4 different JSON documents. Oh, that's your problem. Okay. So I think here we can see everything, right? Can anybody see the screen? Okay, yeah, just a display problem. Yeah. Very good. So it works. Yes. Okay. So now what if we nest both objects and arrays? So now you see I have the key who, that is an array of objects, right? Now it's a nested table. An array of objects is basically a nested table where I have name string and type string. And the way I do that is now in both directions. So I have foo. This is my first object, name Albert, type first, and the second object, name Albert, type last, inside an array, and then ID 1 leaving false. Okay? Who would be able, well, I kind of described it, but who could give me the JSON document for this? Okay, very good. If you can't, try it as an offline exercise. Try it to reconstruct the JSON document, the JSON syntax for these records right there. It's a really good exercise. So you see that now it's actually a nested table. I could represent it as a nested table as well within the cell, right? It's just that since I have a schema and it's always the same structure, I can kind of do it nicely like this, okay? So this is the data frame. And in fact, the Pandas data frames, the Spark data frames, the Spark SQL data frames with C later, this is what it is. This is exactly what it is. These are basically valid collections of JSON documents, collections of valid JSON documents. I just have a few assumptions on JSON. I can actually try to give them to you if I remember. One assumption is that I'm not using open object types, like with the verbose syntax, I could technically allow for any key. Here I don't. It's only these keys right here. That's the first requirement. A second requirement is that I'm not using non-instantiable types. For example, I can say an integer, a string, these are all instantiable types. But if I say type item, which is the topmost type allowing anything, that is not an instantiable type, right? It's an abstract type that is the super type of objects, arrays, and so on. So I'm assuming here that all these types are instantiable, right? Integer, string, Boolean, and so on. Who knows what an instantiable type is in object-oriented programming? In Java, for example, you have the concept of an abstract class. An abstract class can never be instantiated into an object, right? But it can be the superclass of another class. Okay. All right. So this is basically nested arrays, nested objects and arrays, and this is how you can draw that beautifully. But we'll come back to data frames. We'll see them again, but now I wanted to make the connections with JSON. And I have a few more slides actually about this. So now, also continuing to think in an abstract way, we saw that JSON objects are maps. So if I have a collection of JSON objects, technically I have a list of maps, right? From a very abstract perspective. So technically, it means that I can have each object like this on a specific row. Each one of them is a record. Here, it's a flat example. It's all flat. There is only atomic types everywhere, no nested structure. And in that case, I have a nested structure with a nested array that would be an array of objects here and an array of objects. Here, I didn't draw it in the same way. Technically, it's the same thing as this here. Here, it's just that I put them in the header. Here, I put them inside the cell, but it's really the same thing. And this would be a nested data set, right? I have ID1, profession, mathematician. People is an array of objects. The first object is name Ramanujan, living false, and the second object, name Mirzakhani, living false, and so on. All right? Now, I'm giving you the JSON. Now, I prepared actually this one, so you don't need to do it as an offline exercise. This is how I draw them, and this is the original JSON. Who sees that it's the same? Who is convinced that this is really the same thing? More hands? Okay, you can look again offline and compare, but this is really what we are doing here. This is the original JSON. This is the logical view after we have validated it successfully like this, all right? So here I'm contrasting the notion of nestedness on the right and flatness on the left, right? So on the left, everything is flat. On the right, I have nestedness. The other thing you can differentiate with is homogeneous, heterogeneous. Homogeneous means everything is required and you don't have extra fields. On the right, heterogeneous means that some fields can be optional. If living is optional and profession is optional, then you end up with these missing values. You could put nulls if you want to fit it in a relational database, but this is what you could do. And here you see it corresponds to the absence of a key, right? If you see ID3 Turing here, it doesn't have a living and a profession attributes in that case, right? Who is convinced that this is the same? This is the visual, and this is the original JSON. Do you see it, right? Take the time really offline. If you don't see it yet, take the time to look at this. It's very important, right? This is the original JSON, and this is the logical view when we validated it successfully. Okay. And now we can even combine the two with, on the left, something that is flat and homogeneous. Flat because I only have atomic types, nothing nested. Homogeneous because I require all the values in there, and there's nothing empty. And on the right, you have a big mess that is basically nested, heterogeneous. There's no schema at all, so you can basically put random stuff in there. You have, for example, in the first object, an array that has an object and a string, right? So the object name Ramanujan living false, and Mirzakani has a string, right? I think we deserve the break. I can take the question, right? We need to take the break. Right after the break, I'll come to you and we'll start with your question, right? So I'll see you in 15 minutes at 15 past 3.